Good afternoon. My name is Vratislav Blažek. I will be a little bit offset of all your topics, but this presentation was chosen by my colleagues to present it here. More or less, photonic integrated circuits. These are parts of all your experimental setups which you are using, and I want to use this presentation as a guidance for you, which type of components or which type of test and measurement tools use for your setups. EXFO is test and measurement companies. We are starting with physical layer testing, with the research and development setups. It means with multiple grades of tunable laser sources, different parameters with different speeds, but also components for physical layer optical qualification. It means dispersion testing setups, insertion loss, return loss measurements, and this type of setup. We are based in Canada, but we have a big facility in Europe, which is focused to 5G networks and high-speed applications. It means we are more or less covering all real telco applications. Whole presentation. I don't want to be between last presentation and dinner and waste your time. It means I know that this type of testing is completely offset, but I want to show you what is different between electronic integrated circuits and photonic integrated circuits. What are the main differences and how to qualify them.
We are moving to integrated circuits.
Okay, then I can show you real examples from wafer testing and from integrated solution where we use in collaboration with alignment systems from third-party suppliers. When we done pretty big wafer testing with speed which was below 8 hours to test 12 inches wafer with few thousand components on that. In fact, test and measurement need to be aligned with all phases of big testing, or starting from design, foundries, and testing. I mean, more or less, if you look to final this commercial part where you have this component, the 80% of cost is in testing and packaging. I mean, it's not anymore that you are thinking about test and measurement and qualification as completely separate era for you. Testing need to be first what you are designing with alignment system. If you compare that with electrical integrated circuits, they are pretty mature. They have pretty good alignment systems. Pretty easy how to test them with probing systems. With optical peaks, it's more complex. It requires more precise alignments. And you need to think about design of that component before you are starting production. Otherwise, you will waste a lot of money. Testing what all the photonics components which you are producing in a mass production. These are pretty simple structures. These are mainly delay lines, splitters, any type of spectral selective or polarization splitters, Mach center modulators, waveguides, and this type of stuff. It means from optical perspective, this is not rocket science, and it's pretty easy it's pretty easy to qualify them, but how to qualify them with low uncertainty, and how to qualify them with all parameters which you need to guarantee. It means how to provide a parametric qualification of this component. It's every time to define with principal designer of the component what will be tested from start, like insertion loss, like spectral transmission function of the component. If the component is combining optical parameters, how it will be combined with some electrical control parameters or result parameters. I mean, this is, for example, from Mach Zehnder, where first part is from optical, and second part is from control voltage of this Mach Zehnder. Also, the testing of bricks is different when you are doing design of wafer and when you are testing that during manufacturing. The first one, it's more manual way how to qualify the whole design. Second one, it's a quick qualification of all chips, where you will automatically define which chips are passing your thresholds and which you will use for final packaging, which you will sell to your customers. How to test them? If you look to size of pitches on wafer, it's around 125 to 250 microns, and you are doing that from 8 inches on 8 inches up to 15 inches wafer. Alignment system. As I mentioned, you need to think about the design of wafer from day one, because these alignment systems, they are using just fiber arrays which are available on the market. They are with 8 fibers, 16 fibers, or not unlimited number of combinations. It means design of the wafer need to be done from what is available on the market on alignment systems. Electrical is much easier because the pitches are smaller, but it's much easier to locate them. This is easy schematic how to design some component when you have your alignment system, for example, for 6 fibers. Where you are combining optical measurement with electrical. It means you are also adding dummy circuits, for example, how to have quick identification if chip on a wafer is okay. This is a station from Italy, from one customer, which is combining electrical measurement with optical measurement and with alignment system. More or less, this setup is designed to work, for example, for 7 years production. What are standard parametric measurements, or which test kits you potentially use is, for example, optical spectrum analyzer. When you want to qualify power as a function of wavelength, you want to compare that against ITUT grid, where your OSA need to be with some internal qualification or setting of wavelength or referencing of wavelength. This OSA is pretty specific. It can do 2000 nanometers sweep in 1 second. It means it can be used also to qualify pretty quick events which you have, for example, in primary research or in a lab. Next parameters which to qualify is insertion loss or transfer function as a function of wavelength, where we are combining multiple tunable sources, depend which wavelength range you want to test, and it can be also measured with PDL parameters. It means inside is polarization controller, which can do measurement in a multiple polarization, or use it as a scrambler and just use the worst case scenario for polarization. These lasers, these tunable lasers, they are also pretty unique on a market. They have extremely high side mode suppression ratio, around 90 dBs. It means they can be used also for some other application, not only for wafer testing. This is for example of Mach-Zehnder modulator, how it's tested and how it's look like under microscope when you are qualifying that, and these are results measured by OSA versus bias which you are using in this Mach-Zehnder modulator. I mean, this will be typical example after you are qualifying your component. This measurement in case of 8 inches wafer can be done, for example, in this wafer 800 times. It means you need to have really fast solution which is doing this qualification. Depends which type of component you are qualifying. It can be a ring resonator, or it can be easy polarization beam splitter. Based on that, you are using different sources, different detector or different optical spectrum analyzer with some polarization controllers, for example. One of the examples of optical integrated components is, for example, in this case, 40-channel DWDM Max Dmax, where you have 50 gigahertz grid, and you are in a C+L band qualifying insertion loss and return loss of all 40 channels. You have 1/40 splitter, and you are trying as fast as possible to qualify this. That means that it's time to finish. I mentioned a tunable source which is used for qualification of these components. Side mode suppression 90 dBs. Tunable range in 200 nanometers. It means if you look to all telco wavelengths from cutoff up to U-band, it's enough to have three tunable lasers which you will connect together, and you will do equalization of power and hop control in lasers, and you can do one step measurement for all telco wavelengths which are available. This is a measurement of that laser by optical spectrum analyzer. This is how it's look like when you have it in rack in production or in some lab. Thank you. I cut a lot of slides just to not waste your time. Thank you.
Any questions?
I can ask.
No, you cannot.
In fact, I was taking this presentation as a guidance for you. If you have some experimental setups where you need some special sources, where you need whatever type of measurement, let's talk after or now.
Hello, my name is Sergey, and I have a question for you. You have presented several units for testing. I guess most part of them is related to measurement units and to tunable laser units. So we make like big measurement systems combined with some PI, positioners, hexapods. So I haven't understood. Do you have the solution for distributed special? I mean, like with some special resolution.
You mean these alignment systems, or?
No. I mean, like there are several solutions for the waveguide measurement, like provided by General Photonics and Luna. So, do you compete with them?
Yes. This is.
So, do you have the distributed special measurement unit? Or you just have the tunable laser?
You mean like centimeter OTDR or this type of solution?
Yes, or optical vectrum analyzer.
Yes, we have solution which is kind of vector or.
That's a great thing because I think that the competence will bring us to success. Yes.
Okay.
But do you have any information on these units?
You mean for waveguide? Let's keep it for that. I can show you setup. We are not using. We are using slightly different approach to qualify them, but we have in fact production of waveguides is in Czech Republic, which is close to me, and we done this setup for them.
Thank you so much. And